Hello and welcome to the fourth and final video of this series. In this video, we are given a cylindrical cup filled up with water to the level of H sub 0. We are told to derive an expression for the maximum angular frequency that this cup can be rotated to without spilling the contents. So let's go ahead and let's get started. First thing first, I'm going to show or draw a diagram to kind of give you guys a better picture of what is going on in this scenario. So, to start off, we are given a cylindrical cup, and it is filled with contents, in this case water, up to a height of H sub 0. So, this right here, H sub 0, then the maximum height of this cup is big H. And then we're looking from the middle outwards, and this is big R, the maximum that this from the center of the race. And so this is the instance before or at rest, and then from here we're going to give it some angular momentum to the cup and spin the contents inside, and what that would look like, it will end up looking like this. We'll have some sort of parabola looking thing. We'll have this content, the bottom will stay the same as this portion. Then we're going to have this divot where it was before, at its lowest point. This is now depression. I'll make this blue actually. And then this is the maximum height at which it was earlier, over here. And then this is the different H's that we'll be solving for at the different distances along the radius, right? Depending on R. So we'll be solving expressions for the depression and the height of the water, the fluid. We'll be using those two derivations to then give us a derivation for the maximum angular momentum that we can give to this cup. So I'm going to go ahead and get started with the what we did in the previous video with the generic equation for fluid statics, which is simply the change in pressure with respect to change in distance is simply equal to rho acceleration. And since we're spinning this cup, we know what the acceleration is. We know that we have a centrifugal acceleration, right? We know that A is simply equal to omega squared R, so that we can rewrite this as the change in pressure with respect to the change in Z is equal to rho omega squared R. However, we're not using dz. We're not using dz. We're using, with respect to R, we're using a radius, so then we can rewrite this ahead with rho omega squared R dr. And then you can go ahead and integrate both sides out. And then, of course, these are W variables, right? For the left-hand side, what we're going to be using is P1, which is at this point, the bottom, right? And then P2, or P, which is when it was at the top. And then for a radius, we're going to do the same thing. Big R and little r. R1 is right here, and then R is at the maximum value R could be, which is the outside. So we can go ahead and rewrite this as dP1 is just simply P minus P1. And then we do this, we write out the constants, rho omega squared, and we had R, so the derivative of that is 1/2 R squared. So then we plug that in with R, so 1/2 R squared minus 1/2 R1 squared. Then, however, P1 at this point would be 0 because of the atmospheric pressure being 0. So we can cross this out as being P is equal to rho omega squared. And then here again, radius 1 is going to be 0 because R1 is at the center where R is 0. So we can cross this out as well. We can rewrite this as rho omega squared, R squared all over 2. Right? Then now what we can do is we can utilize the buoyancy equation to then equalize them two out and rewrite this expression in terms of H. So if you guys remember buoyancy's equation, simply rho GH, okay? Make these equal each other, so then we have rho omega squared R squared all over 2 is going to be equal rho GH. So then if we cross this out, use blue, this cancels out, and everything remains the same, so that we end up for a value of H, that we get H is equal to omega squared R squared over 2G. And that's our derivation for H. Now what we want to do is get our derivation for the depression, and then put those two together to get our value for the maximum angular momentum for this concept. So then for the depression, what we're going to do, we're going to be solving in terms of volume for V, as we know that the volume remains constant throughout these two different instances, as we know that the total volume in this section at the beginning is going to be equal to the volume in this section up here, right? Let me fix this up a little bit so you can see a little better. There we go. And so for the volume we have with this, we can equal it as simply the cross-sectional area multiplied by the height, right? In cross-sectional area here, we know that it's a cylindrical, so we know R, and we can simply rewrite this as pi r squared. And then for the height, we're not going to be using HO or H, but we're going to be using D for the depression, right? As this is the change between these two heights. Right? And then for the other instance, we're going to equal it to is we're going to think in a little bit different perspective. So if we're going to make this in different slices, different subsections of the height, if we're going to look at this on a top-down view, this is what we would see with the different proportional value of R, and then as R increases, you get larger upon the circle, and this area right here is just simply the change in the radius proportional to area, so I'm just going to call this dr. We're going to do the same idea that we had here to solve for the volume, simply the area times the height. So what we're going to have to do is we're going to equal the, write this just under, the change in area is simply equal to the circumference of what we're using multiplied by the width, which is dr. So we're using 2 pi r times dr. And then like we said, if we want to do what we did here, we have to multiply it by the height to get the volume. So change of volume is equal to 2 pi hr dr. And then we can go ahead and substitute these in to solve for each other and get for an expression for the depression. Sorry. So then when we go ahead and rewrite this, we get pi r squared d is equal to the and then we're gonna have to get the integral of this. So I'm gonna write this in blue. Integral of 2 pi hr dh, and then what we can do here is we can plug in h for plug in these values for h, but for right now I'm just going to write 2 pi r h dr. And so we can go ahead and rewrite this for h, so that we get pi r squared times d is equal to I'm just going to So we get 2 pi h is that, divided by 2 divided by 2, so we get, with r, so squared, r becomes cubed, and then we have g under respect to r. Alright, then we can go ahead and take the constants out of this, so that we can go ahead and rewrite this again. Pi r squared times d is equal to omega squared over g r cubed dr. And then we're going to be deriving this, let me make sure that we're using dummy variables again. We'll be deriving this expression from r sub 1 to big R. And r sub 1, again, remember, is when r is equal to 0, when it's right in the middle, and big R is when we're at the outside of this circle. So you go ahead and rewrite this again. Pi r squared d is equal to w squared over g. And then I'm going to be rewriting this. R cubed is going to be 1/4 r to the 4. So then 1/4 big R to the 4th minus, and then like I said, r sub 1 is going to be 0, so there's no point. I'm just going to close it off and rewrite this off again. As you can see, we have some common denominators in the numbers. So what we can do is just write r squared off both sides so that we get value for d, for the depression, to be omega squared and then multiply by r squared by g. So I kind of lost this pi somewhere here. So there should be no pi. It should simply be for g, I believe. Yeah. So let me go ahead and rewrite this on this side so we can make a little bit more space and rewrite everything. Omega squared. Squared over 2g, then depression equal to big R squared over 4g. So there you have our two expressions, derivations, and that we'll end up using to solve for the maximum angular momentum. Go ahead and make some space now. So then now, let's rewrite this expressions solving for the maximum height of the cup, so that we can then get the maximum momentum. We can solve this to be as do h sub 0 minus the depression. Then we get this little part, subtraction under, plus the maximum height. So we get h sub 0 minus the depression, plus what I say, we're using h max. What we're going to do is going to plug in these two equations for our d and for h max. So that then we get h is equal to HO minus, and then D, plug that in so that we get omega squared R squared over 2G plus omega squared R squared over 4G. If you guys can see, these two are pretty much the same things if we just take out these 2 and this 4, these are the same expressions, right? The omega squared r squared all over g, right? So that we get capital H is equal to H naught minus, we have is 1/4 minus 1/2, so we have a positive 1/2 of this expression, which is omega squared r squared over g. Alright, then now finally we can go ahead and rewrite this expression in terms for angular momentum so we can solve for it. So that we get omega squared r squared over 2g is equal to h minus sum naught, multiply everything by 2g over r squared so that we get omega squared is equal to h minus h sub naught multiplied by 2g over r squared. So then if we go grab the square root of this, sorry, this should be a 1/4, because 1/4 minus 1/2 is 1/4. Sorry, I apologize for that. So all this should be 1/4. Starting to run out of room. I'm going to bring this over here. I'm going to rewrite this again so you guys can see a little bit better. We have angular momentum squared is equal to h, capital H minus h sub naught multiplied by 4g over r squared. Right, and then now we only have to find the square root of both sides to get the angular momentum. So we get the angular momentum is simply equal to, let's do square root of 4g over r squared. We get 2 over r multiplied by square root of h minus h sub naught multiplied by g. So we can go ahead and rewrite this as the angular momentum is equal to 2 of the square root of h minus h sub naught multiplied by g all over big R. There we have it, our derivation for our maximum angular momentum for which the contents, which in this case water, within this cup would not exit out of the cup. So there we have it. Hopefully you guys enjoyed this video, and I hope you guys have a good rest of your afternoon.